Hey, good evening, everyone. This is going to be a quick lesson on neural networks. So this is just going to be a really introductory level, going to kind of talk about the background a little bit, the theory around how they work, though I'm going to leave most of that to a video recommendation I have for you guys. And then we're just going to do a really simple example. Neural networks can be kind of intimidating, and so we're just going to do a really simple example to show you that you have the ability to kind of go in there and test things out and do it yourselves. So that's our goal, is to do an introduction, do a really quick example, and we'll see if we can get wrapped up in 15 or 20 minutes here. So like I mentioned, I would start by watching this video. What happens? There we go. The video is from 3 Blue, 1 Brown. It's an introduction to neural networks. There's a second one in the series about gradient descent. It's a YouTube channel I'm always recommending to people. Love this YouTube channel. This is a good introduction to exactly what a neural network is and how it works. So I'm going to give you a chance to watch that if you haven't already. Go ahead and head over there. I'll be linking it on the Slack and this video description. So watch that for a good introduction to neural networks. And then to just kind of recap some of the important things from that video, we have a nice little picture of a neuron here. So our neural networks are made up of little pieces that are sort of analogous to a neuron in a human brain, and they're called perceptrons. And so a perceptron is made up of a couple parts. So it's like a algorithm unique to itself, this perceptron algorithm. And it's made up of a couple parts. It takes in an input. So what's happening in this picture here is these are all the inputs. So your perceptron is taking in inputs from other perceptrons, and that's this x1, x2, xm here. It's multiplying them by their own weight. So whenever it gets an input from the first or the 0th input here, it multiplies it by the corresponding weight. These all have their own weights, and these weights are actually what our neural network is learning when it goes through the learning process. So we're going to have, in some cases, literally millions or billions of these weights, thousands of these perceptrons, of these neurons, each with a bunch of weights, so millions of weights. And these weights we're figuring out the exact configuration for these weights that'll let our model do the task that it's trying to do. So we have these weights. These are all multiplied and then added together. And then it's fed into an activation function. And then that activation function feeds into the output, which goes to the next neuron down the line. So that's what a perceptron is. All it is set of weights, multiplies those weights by the inputs, feeds it into an activation function, and then spits out an output. So our neural network is made up of multiple layers of these perceptrons. So each of these circles here is a perceptron. So in one layer, we might have like 64, 128, maybe even up to 1,000 of these individual perceptrons. That's in one layer. They're each taking input from the layer previous, and then they're each giving output to the next layer. So the second layer is also made up. It can be the same number, it can be a different number of neurons. So, we've got a couple hundred in our first layer, got another couple hundred in our next layer. They're all connected to each other. So each of these neurons is feeding into each of these neurons in the second layer. And then we can have multiple of these inner layers. And then finally, we feed into the last layer, that's our output layer. That actually outputs our model. So when we're talking about a neural network, we talk about layers. Each of those layers is made itself up of multiple neurons or perceptrons, and altogether that make up our network. You'll also hear a lot of talk about the gradient descent algorithm. And so that's the algorithm that we use to actually figure out how to update these weights. It takes the derivative of the loss function, propagates it backwards, but we won't get into details of how that works, but just know that when you're hearing people talk about backpropagation and gradient descent, they're talking about the algorithm that we use to train these neural networks. So I'm going to hop over to Colab. I do all of the work I do with neural networks, I do in Colab. because they give you can go to change runtime type here and use a GPU to accelerate the training process. So that's really nice that they give you that free GPU. So that's why I like to do the work in Colabs here. We won't need a GPU for our quick example. But whenever you're doing something a little bit bigger than what we're doing, that's a good idea. So the nice thing about neural networks is that we're using Keras, the package Keras, to build them. Keras is connected with TensorFlow. You can see here the other big sort of framework is PyTorch, which I haven't worked as much in, so we're going to be using TensorFlow. And Keras is very similar to scikit-learn. You'll see a lot of this sort of same syntax, even if it's not exactly the same. So you should already be familiar with the sort of details of how we're going to initiate our model object and then fit to train it. So that's nice. You've probably heard, about neural networks being used for image classification. So that's kind of why they've become so popular, is because of their huge advantages being able to recognize images. But we can use them for any sort of classification or regression problem not related to images as well. And so that's what we're going to be doing in this example. We're going to be looking at the same cancer data set that we looked at in last class and trying to do some classification of breast cancer as malignant or benign based on these features here. So yeah, let's get into it. So import our libraries. The new ones here are these Keras models sequential and Keras layers dense. We'll talk more about that in a second. We're using this function here to load a data frame. It loads it not as a data frame, I misspoke there, but as a dictionary. So we can look at the keys here. So we have our data, our target names, description, feature names, file name. So if we look at our target names, should be malignant and benign, which it is. If we look at our feature names, these are the 30 features. These will be the columns in our data frame. We can look at the description and see that it came from University of Wisconsin. Actually, I don't know if it's University of Wisconsin, somewhere in Wisconsin. Gives the description of what's going on in the data set for us, so that's nice. All right, we're going to convert this data set to a data frame by just calling the pd.dataframe function on the data part of that dictionary. We're going to tell it that the columns are in this feature names part of that dictionary. And then if we look at the head of our data frame, looks like it all imported correctly. Here's all of the features we're going to be using. We can take a look at the shape of it. We've got 569 instances, 30 columns. 569 is not a lot. Usually with neural networks, you want examples in the like tens of thousands, hundreds of thousands. But in that case, it would take a lot longer to train, and I would be sitting here recording this video waiting for neural network to train, which I did not want. So that's okay that we have a smaller one for this. But checking if we have any null values here, and it looks like they all match up and they're all floats, which is great. So we're about ready to get started. Our target is going to be pulling the target column out of the dictionary. Should have the same length and be only one column, which it does. And now we're doing our train test split, which y'all are very familiar with. So we're just feeding in our cancer data frame and our target. We're stratifying on the target, so we'll have an equal number of malignant and benign in each split, which is good because I think it was a little bit imbalanced. And we're taking 75% of our data for a training set. So if we do that, so X train, X test, so that X is our features, so those should both be 30, that's good. Y train, Y test, these numbers match up, these are both 1, so it looks like didn't make any errors there. We are also going to scale our data, so we've talked about scaling our data and why that's important. We've seen this a bunch, so we have our standard scaler here. Notice that we are fitting it to our training data and only transforming our test data. There's no fit on this test data here. That's something we've kind of glossed over, but is best practice to only fit it to the trained data and then transform the test data without fitting to the test data as well. All right, great. So now we're into the new material on how to actually make this neural network. So the first piece is we're going to initialize our model object, and this is the same. This should look the same as if we were doing like model equals, you know, scikit-learn's linear regression or something like that. So we're initializing it to this sequential, which we imported at the beginning from Keras. But now it's going to get a little bit different. And so we actually need to build this neural network out. So when we were using decision trees or when we were using different types of regression, that was all under the hood. But now we have to specify the architecture of our neural network here. And we're going to start with a simple architecture. We're just going to have one layer. So if we go back here, we're just going to have an input layer and an output layer. So we don't even have any hidden layers in the middle here. So this input layer is, so these layers of perceptrons, these layers of neurons are called dense layers. So our first layer is this dense layer. This first number here is the number of actual neurons we want in that layer. So we're going to have 50 neurons in our first layer here. The second thing is the activation function. ReLUs are the most popular activation function currently. So I would just recommend always using ReLU. I can't think of a situation where you would want to use something else. If you want to, a new popular variant on ReLUs is called leaky ReLUs. And there's other activation functions out there. But again, this is intended to be a simple introduction, and for our purposes, ReLUs will work almost all the time. And again, this activation layer, this activation part of this dense layer is this piece here. It's the activation function. So after you add up all the inputs, you feed it into the activation function. And what the ReLUs is going to do is it's going to take any value less than 0. It's just going to take it to 0. And any value greater than 0, it's going to be the identity function. Let me actually look at let me pull up a picture for you real quick. So any values below 0 takes to 0. Any values above 0, it's the identity function, just returns that. So that's what this activation is doing here. And then this is important, the input dimension has to match the dimension of the data we're feeding in. So let's go ahead and see. We change this input dimension, we'll get an error. Nope, we might not get it till we fit. Yeah, so we just get an error alerting us that we expected it to have shape 20, but got shape 30. So that's what's going on there. This can happen a lot if you're kind of copying architecture from another source with a different input dimension. You might get this error. All you need to do is go in here to this input dimension parameter and make sure it matches up. And that's kind of what I always do is, this is a really simple architecture, but rather than try to design architectures myself, there's a lot of smart people out there working on that problem. So I'm always borrowing architectures from other places. So that's our first layer, that's our input layer. We could add some more dense layers if we wanted here. In general, more dense layers let your model train better, let your model get accuracy gains, but it'll take longer to train. So if we wanted to add more dense layers, this is all we'd have to do. We don't need an input dimension in these second ones. So we could even add 2 hidden layers if we wanted to. And then the important thing is that you have this output layer on the end. And the output layer has a couple of tricky things, and it depends on what you're using the network for. We're using the network for classification. We're trying to classify these 2 types of breast cancers. And so since it's a binary classification problem, we have only 1 neuron in our output layer here. If it was a multiple So if we had like 5 classes that we were trying to classify into, that number would be different. And I think it's just equal to the number of classes, but now I'm second guessing myself because that binary classification is 1. So now I'm worried that it's like number of classes minus 1, something like that. So we're going to get a quick, we're going to quickly double check ourselves here. So we've got 3 here, but I don't know what we're actually classifying. Okay, cool. So they're doing this classic iris data set. So yeah, a little bit of a mismatch if you're doing, so if you're doing a classification with classes more than 2, you'll just have the number of classes here. So if you're doing that iris data set with 3 classes, you would just put a 3. You've got 10 classes in your data set, you would put a 10. But with 2 classes, we only need 1. I'll have to think about why that is. If you're curious, let me know and we'll figure it out together. So that's the first part of this activation layer, is you need to put the right number in here. And let's just see what kind of error we get if it's not the right number. So we get an error when checking target, expected to have shape 2, but got array with shape 1. So that'll tell you the same thing here. That'll alert you to what number you need there. The second thing is, you notice we have a different activation function here. So the activation function for the last layer is different, and it depends on what exactly you're doing again. And so here we have a sigmoid. I think sigmoid will work for any sort of classification. There are some other options. Keris's documentation page is really good. It's got a lot of the activation functions here. Softmax is what you're going to want to use if you're doing classification with that's not binary, that has more than 2 classes. Let me see if there's anything else. There's our value function that we're using. There's a sigmoid function that we're using in our output layer. Yeah, so sigmoid for binary, use this softmax if you're classifying more than 2 things. Great, so that's our neural network. We've added 4 layers here. There's all sorts of, as you start to look more into these architectures, there's more layers that you can add besides just this dense layer. Dropout layers are an important one. But for a simple model, this will get us started. And then as you get more interested, you can explore some of those other layers. Now we need to call this compile function. And so what that's going to do is it's actually going to put all these layers together for us. We need to give it a couple things. We need to give it a loss function. So the loss function is what it's using. It's the same as the loss function that we talked about in regression and things like that. That's what the model is using to kind of penalize errors and things like that. So we're using binary cross entropy. The binary, again, because notice a lot of these depend on how many classes we have. We have 2 classes. We're doing a binary classification, so we have binary cross entropy. If you're doing more than 2 classes, it would be categorical cross entropy. This is for if your variables are 1 hot encoded. If you just have integers, so if your classes are like number 1, number 2, number 3, number 4, number 5, it's sparse categorical cross entropy. But we're using binary cross entropy. And then the optimizer is the algorithm it's using to calculate those derivatives, do that backpropagation and that gradient descent. And we're using SGD, which stands for stochastic gradient descent. So we're just using the classic gradient descent algorithm, and that'll be good for us. But other good ones are, so there's an optimizers page here, just like there was for the activation functions. Some other good ones, RMS prop is good. And I usually use Atom is my kind of all-purpose optimizer. But we'll stick with the classic stochastic gradient descent for this one. And then we're telling it that we want it to report accuracy. So we'll compile that again. And now, so that compile function was new. So this should look familiar from the models we've been training. This should look familiar, at least the first half of this, from the models we've been training. But we had to add these specific layers in. And again, I would normally just go to some outside source to find a good architecture. And then we had to remember to compile our model with this loss and this optimizer here. And now we're going to fit it. So we're fitting it X trained, Y trained. That's exactly the same as we fit all our other models. The new thing here is epochs. And so that's how many times we're going to go back over the training data. So each epoch will take all of the training data in, but we'll get more accuracy the more data we feed into the model. Neural networks are very data hungry, so they need a lot of data. So we're going to feed in the data into our model 100 times. And then this is nice. This neural network, you can build the validation right in. So notice we didn't do a validation split up here. It's going to build that in for us, which is nice. And this verbose just gives you kind of updates as it's running. So this is what it looks like when it actually trains. And this went super fast because we have so little data. Normally, like it took 0 seconds here. Normally this might take like a couple minutes. And so if it's taking a couple minutes each epoch, then that'll add up. But this was nice. So it gives you your training loss, it gives you your accuracy, and then it gives you your validation loss and accuracy. So you can see the accuracy go up here over time. So the accuracy was only 47% to start, then it jumped up to 75, 88, and then we've kind of got it slowly going up here. 96, 97, 98, and it looks like we peak out at 98 with a validation accuracy also of 98. Great, and then so our model's trained. Once it reaches 100 out of 100, it's trained. We can evaluate it. Got a test accuracy of 98%, which is, sorry, that was training accuracy of 98%. Let's see how we did on the test. Only 95%, so not quite as good as trained, but that's all right. And there we go. I think we'll stop there. That was our introduction to neural networks. Hope that was helpful. See you guys soon.